Thank you very much for coming. It's great to have all of you here, and many thanks to Zyverge for organizing this event. And in this talk, I'll show you how we solved the problem of schema evolution and backwards compatibility by building a full-fledged compiler in Scala. This compiler is called Baboon, and it does the monkey job, and it does it very well. If you want to ask a question, there will be a Q&A session at the end, and we may catch up on Discord. So first of all, let me introduce myself. My name is Pavel. I'm from Septimal Mind, an Irish software development consultancy. We focus on productivity and team efficiency, and we are big fans of Scala and pure functional programming. We participate in a variety of open source Scala projects and contribute to them. If you use Scala, most likely you use our contributions directly or indirectly, and you have our code in your class path. Our notable projects include dstage, the best dependency injection tool ever, Izumi Reflect, the portable reflection macro, Bio, the tagless final hierarchy for bfunctors, and Logstage, the effortless structural logging framework. Some of you might want to ask me about Grandmaster, our build tool for Scala. Unfortunately, we hadn't enough time during this year to make a substantial progress on that project, so you would have to be patient. As I said, we make teams productive. There are many things which hold teams back, but there is one important blocker we face multiple times. The code responsible for defining interfaces at the boundaries of the product components, or in other words, the code responsible for communication for various aspects of remote procedure calls, may easily comprise up to 90% of the whole code base. Just think about it. In extreme cases, up to 90% of the code is just about wiring and plumbing, not about actual business logic. And well, for some reason, it's the integration that is really painful and holds us back. The picture on this slide shows how ChatGPT sees integration of a complex enterprise project. Over the last 15 years, we made multiple attempts to make integration less painful and more enjoyable. We trialed virtually every RPC technology and approach out there, starting from as far as WSDL, continuing with semi-formal technologies like GraphQL and Swagger, and ending with formal things like Thrift, Protobuf, and Kappan Proto. As a part of that effort, we designed several data and interface definition languages. Our first attempt is called IdeaLingua. It was a successful prototype of a nice and ergonomic RPC language, which managed to alleviate a lot of our customers' pain. Although that was our first attempt to make a production-ready compiler. We were inexperienced and made a lot of mistakes. So while the compiler worked, it was a nightmare to maintain and extend it. Later, we decided to do a complete rewrite with a nice, clean, and concise design, considering all the shortcomings of our first attempt. That new IdeaLingua includes a lot of powerful features. For instance, two forms of inheritance, both nominal and structural, and even real-type constructors, which lay somewhere in between C++ templates and Java generics. So, once we implemented IdeaLingua, we and our customers were happy until a nasty thing happened. Data models tend to evolve over time, and sometimes stupid compatibility incidents may happen. While IdeaLingua has some basic data evolution capabilities, it was not designed around the idea of bulletproof backward compatibility. Although our customers didn't worry much, we relied on various tests, and everything was fine for years until it wasn't. Two snippets on this slide show a simplified version of what happened. Can you spot an issue there? A developer renamed a field and kept the old field for compatibility purposes, but forgot to make the new field optional. Usually that would be discovered during testing, although in this particular case, our thing backfired. The team wanted to make some things lazy to reduce load times, and refactoring happened in a transient data structure, which was relatively rarely serialized. But when the code reached production, there were thousands of furious users who completely lost their data because there was one more improperly handled corner case, and the code mistreated the serialization exception and reinitialized the storage. So our customer lost a fair amount of money and reputation, and they wanted us to design a bulletproof solution which would prevent their engineers from writing fragile code and prevent any such incidents from happening. We decided to create a new nice little language built solely for schema evaluation purposes. We were under immense time pressure, so we had to limit the features to what was really necessary for one particular use case of one particular customer. This language allows you to define a set of data structures organized into namespaces and versioned by global version tag. It supports, includes, and allows you to use native data types of your target language when necessary. The language supports records, which are just ordered sets of fields, algebraic data types, and separately simple C-style enumerations. As I said, the records are sets of fields, and they support structural inheritance with all the standard set operations. Like you may add a field to a record, you may add all fields from some other record to a record, you may remove a field or all the fields contained in another record. And there is an odd but useful operation set intersection, which leaves the structure only with the fields which are present in the intersection of field sets of two other records. Also, there is a very limited support for nominal inheritance. The ADT members can be marked with so-called contracts, which behave like sealed traits in Scala and are rendered into closed nominal inheritance hierarchies. The primary purpose of the Baboon language was to make data evaluations as easy as possible. When you modify a data record, there might be three primary ways to read an instance of an old record version into the new one. In many individual cases, the conversion can be done automatically. For example, when you expand the range of a numeric type, or make a regular field optional, or replace a list with a set, or vice versa. Or when you remove a field or add an optional field or a list field. Baboon recognizes many of such cases and can even compose the rules. So you may replace a list of short unsigned integers with a set of unsigned integers, and Baboon will generate a conversion rule for you. In some other cases, there is no sane way to derive conversion automatically. For example, when you add a non-optional field or change a type to something definitely incompatible. In that case, Baboon will generate a conversion stub for you and make sure that you provided an instance in runtime. There also are some borderline cases, like when you replace a string with a list of strings. In such cases, Baboon opts to enforce manual conversions. Apart from the conversions, Baboon also generates codecs for two serialization formats. The first one is JSON, and there is nothing to discuss about it. It's just boring. The other format is a custom tagless binary format, which we call UIBA, or ultra-efficient binary aggregates. UIBA does not contain any metadata unless it's strictly necessary. UIBA blobs are just pure data in binary form. The only exceptions are prefix length encoding for variable length data types like arrays and strings, and our exception is branch tag for algebraic data types. So on the slide, you see that I've encoded a rect branch of an ADT into a binary representation. The first byte is the branch index, when comes the length of the name field, and when to 4-byte integers. And that's it, just like in protobuf and cap-and-proto. So let's make a short overview of what we learned. The Baboon language supports records, algebraic data types, and enums. It considers records to be sets of fields and supports structural inheritance with all the set operations, including intersections. Also, it supports a very limited version of nominal inheritance. It can automatically derive JSON codecs and binary codecs for a custom format we call UIBA. Baboon excels at data schema evolution. It can automatically derive conversions for many data evolution cases and makes sure that all the required non-trivial conversions are provided. It supports namespaces, inclusions, and basic type constructors, namely sets, lists, dictionaries, and optionals. Also, Baboon lets you mark your types with root keyword and eliminates everything that's not reachable from the root. And it may show you which type definitions were eliminated. That's a nice way to keep your code cleaner. Currently, Baboon targets only one platform, C#, but more platforms will be supported. And also, we have a nice syntax highlighter for Visual Studio Code. So, I promised you to show how we can use Scala to build real compilers. Most of the time, engineers prefer to not even think about building their own programming languages, even domain-specific ones. We tend to think that that's too hard and never worth the effort. In fact, the first working prototype of Baboon was built in less than 2 weeks. So you would ask me, how did we do it? How would you build a compiler? So we'll take fast parser when we write a big chunk of magical code and job done. It works, but I guess that's a bit too generic. So let's try to have a deeper look. Many concepts we are going to discuss would be applicable to a wide range of compilers and transpilers for various languages, including general purpose ones. Many compilers are built around the idea of passes. You start by parsing your program into a mutable syntax tree, and when you traverse your tree multiple times, adding things here and there, and once you can progress further, the job is done. If all the contracts are fulfilled, the compilation is successful, and if something is missing, it's an error. The idea of passes assumes that you have one huge universal representation, which is mutable and can represent all the possible intermediate states of your compilation process. While this idea is omnipresent, we find it counterproductive. And instead, we prefer to use so-called phases. Each phase is a pure function which takes an immutable data structure of a particular type, processes it, and returns another data structure of a different type. The pipeline of the Baboon compiler consists of 10 phases, which are parsing, inclusion resolution, namespace processing, type reference resolution, formation of an acyclic graph of type definitions, type definition processing, verification, templating, import resolution, and finally rendering of the output code. So let's walk through these phases. There isn't actually much to say about parsing. FastParse is an awesome library. It has its own quirks and kinks and loves to throw warnings which are hard to get rid of, but it allows you to quickly build unambiguous parsers which tend to work exactly as you want them to and to never get into infinite recursion. If you want to use FastParse, I would advise you to build a hierarchy of case classes and sealed traits closely representing your syntax. It should provide you a certain level of abstraction. For example, it should definitely ignore formatting and indentation, and most likely it might ignore comments. We may call such tree a raw abstract syntax tree. When we should write FastParse rules and don't be afraid of borrowing ideas here and there. And also, I would advise you to attach metadata like line numbers and file names to every node of your syntax tree. That would be invaluable when you start working on human-readable errors and warnings. So the next phase is inclusion resolution. I might say that it's a very bad idea to attempt using C-style raw text inclusions. In my opinion, the most efficient way would be to recursively parse every inclusion into a raw syntax tree, and then fold them back into one single tree, replacing inclusion nodes with corresponding trees. Don't forget to add a safeguard for circular inclusion chains. Next two phases are namespace processing and type reference resolution. And in fact, these phases are the most important ones. The way you approach them significantly affects the complexity and limitations of your compiler. So let's assume that we have a typical language which supports nested namespaces. Definitions in one namespace might reference definitions from other namespaces and may use incomplete prefixes to disambiguate. On the slide, I have a top-level definition of a record named A, a top-level namespace named outer, which has another A defined in it. And also it has a nested namespace named inner with a record named B, which references some type named A in two different ways. When we look at this code, we might assume that both fields in B reference record A defined inside of the outer namespace. That is sound and logical. Although it might be not that obvious for our program when it meets some reference to a type named A somewhere in the tree, but has no idea where does it come from. Many classic approaches assume that every time we meet a reference, we might run a recursive search for it, but that's extremely inefficient. But also, but we may notice that namespaces form a lookup tree, or in other words, a prefix tree. So if we build a prefix tree out of our raw syntax tree, when we traverse our raw syntax tree once, doing prefix tree lookups every time we meet a type reference, we would be able to efficiently resolve every reference. This statement won't hold if we have advanced type constructors, even in forms of generics or C++ style templates. In that case, we would have to roll back to classic recursion every time we meet a template. Idealingua does exactly that, but Baboon does not support templates. Next phase is also very important, and this is where our design diverges from the classic approaches. We might notice that type definitions form a graph. So in order to figure out which fields a record contains, we need to know the content of all its structural parents. So we cannot process a type definition until we processed all its parents. At the same time, we may note that regular type references in the fields do not introduce dependencies. So if we explicitly build a graph out of our type definitions, correct. So if we explicitly create a graph out of our type definitions where inheritance relationship is represented by graph edges, when check that the graph is acyclic, we might topologically sort it and process definitions in a single pass without using any recursion at all. This is actually the simplest and the most natural and the most efficient way to process a complex data structure. And it's the same idea upon which our dependency injection framework, dstage, is built. And in fact, it even shares the same code. Again, complex type constructors do not align with this idea. If your language supports them, you might have to recurse to recursion. But again, it's possible to limit it only to the cases where it's strictly necessary. The next phase is verification. I would advise to use any kind of an error accumulating data structure and just write a bunch of checks which return units when everything is fine, and accumulators when something is wrong. If you want to support warnings, you might do the same. The checks should be pure functions, so you don't actually need any complex structures like zio, cuts, or even scalactic. A simple either will suffice. In Izumi, we have several simple syntactic extensions which make it easy to use either as an error accumulating data structure. The last part, sorry. The last part I want to talk about is the synthesis of the output code. There are two typical approaches: untyped template engines and typed syntax tree builders, like Scala Meta. And both approaches are far from being perfect. When you concatenate strings, you can't process them further. Even indentation might be a pain. And typed syntax tree builders like Scala Meta are heavy, might have cumbersome APIs, might not work on Scala tree, or may not exist for the language you want to support on your transpiler like Go. There is one common case for transpilers which does not actually fit well into both approaches. So let's assume that we are composing a program which references two types with the same name coming from two different packages. Of course, we might always use fully qualified names if our target language supports them. But even if it does, we make our code unreadable. So before we can produce our output, we need to produce our output. Before we can write the import section, we need to know all the types which are referenced in this particular compilation unit, which we are about to synthesize. So, as a part of Izumi project, we created a templating engine which represents the text you work with as a tree with text nodes, transformation nodes. The most common transformation is indentation, and value nodes. When we need to reference a type, we insert the type reference as a value node. And when we have a chance to produce a nice and unambiguous import section. And when we can render our output program with nice, clean, and readable type references. So, in a conclusion, I would like to say that Scala is a truly awesome language for writing real compilers quickly and efficiently. If you use multi-phase design and organize your type definitions into graphs, you may save yourself a lot of time and effort, not sacrificing anything. Baboon is already a great data modeling and schema evolution language with simple design and clear code. Currently, it only supports C# as its target platform, and we want to support more platforms. If you ever faced issues with backward compatibility and schema evolution, and if you ever wanted to participate in a compiler development, it's a good chance to join our project as a contributor.